So what we're studying in this experiment, first, we are understanding what viscosity is, then how viscosity changes with temperature, and we'll learn a little bit about different ways of measuring viscosity and pick one for our experiment. So definitely, in a broad sense, two different sets of experiment. One, just figuring out the viscosity, and second, figuring out the viscosity with temperature, how it changes with temperature. And as one of you guys already answered what viscosity is, it's a property of a fluid that is defined as the resistance to flow. Meaning, if you want to move a fluid from point A to point B, you need to apply some force. You need to work against some resistance, and that resistance is viscosity. Now, the more the resistance is, the harder it is to move the fluid, and this is where comes the thickness, right? The more the viscosity is, the more thick the liquid is. For example, honey is more viscous than liquid. Now, you can compare viscosity with modulus of elasticity for a solid. How can you do that? Let's say this is your liquid. This is a solid. It's a solid body which is stuck between two plates, and they have a area of A. This bottom plate is still, and you're applying some force on the top plate, which is P. All right. Sorry, you're applying some pressure on the top plate, which is P. You can call it shear stress, right? Now, what your intuition is telling you, if it's a solid, and if the bottom plate is steel, if you're pushing the top plate in a certain direction, then definitely your solid will have some sort of deformation, right? If this is your body, if this is your boundary of the solid, they'll be like that, right? The bottom one will retain the initial shape, and the top one, they will move on to another position, which you call strain. Now, like solid, in the liquid as well, you would see strain or change in dimension. However, a solid specimen, it offers a property which is a solid, meaning its particles will be in the fixed distance from each other over the time. Now, liquid doesn't offer you any property like that, because you all know that liquid doesn't have a shape. Wherever you put it, it's going to take the shape of the vessel. So the definition of strain, what's telling you that the difference of dimension between the initial length and the final length is strain, right? But the concept of initial length doesn't have any significance when it comes to liquid, because it's constantly changing. So what you can do, you can take from an infinite or a big time frame, you can take a small time frame for your experiment, and you can measure how much change I'm seeing within that small time frame, and I can assume that change is only happening because of the external force that I'm applying in that small, tiny time frame. So you can say when we measure strain for solid material, when it comes to liquid, we measure strain rate, right? Or how much a particle or a layer of a liquid moves from point A to point B in a very small time frame, and what's the rate of it. So if you guys remember from your earlier studies, what's modulus of elasticity, which will be shearing stress over just strain. But when it comes to liquid, you have the shearing stress over shear strain rate. Okay. Now, imagine using this property in a mathematical calculation everywhere. Now, if you have a very straightforward relation between stress and strain, if you can say that, hey, however much stress I put, my strain goes up proportionally. Okay, so all you need to use is this equation, y equals to mx, and you need to find out the m, the viscosity. And if you can find that, you know that's a constant. Only if you can find that, then all you have to know to figure out what's the strain rate or the strain is just plug them in this equation, measure the stress or how much force you are applying, and you can figure out the strain. So this straightforward assumption of liquid property, and the liquids who carry out this assumption, we call them Newtonian liquid. The more stress you put, the more strain you see, and the slope is linear, or you can say unit or 1. However, that's not the reality. In reality, it's not so straightforward of a relationship. The more stress you put, for some liquid, you would see that the strain rate is getting lower, meaning it's getting harder to move particles around the more force you put. That's called shear thickening, like your liquid is getting more and more thick. The opposite happens, it's shear thinning. And then Binghamton plastic, where you don't see a certain amount of strain for a certain amount of stress, and after that it starts giving a linear profile. But in our study, we'll mostly work with non-Newtonian, because that's the realistic oil or liquid that you'll have to deal with in your carrier. Any questions so far? Okay. So why viscosity is important, right? It's important because it gives you two different properties. It tells you how much force you need to start moving a still liquid, and how much force you need to keep it moving at a certain flow rate, right? And these properties are very important in fluid dynamics, because we use these properties all day, every day, everywhere. In your vehicles, you use lubricants. In your vehicles, your fuel goes from your tank to your combustion chamber through some lines, right? So definitely how much fuel is getting into a combustion chamber is defined by the viscosity of it. The easier it's, the thinner it is, the less viscosity it has, the easier it will be to flow the liquid, right? So that's one example. There are hundreds of examples like that. For example, lubrication. When you're lubricating your bearings of a vehicle or a machine part, the lubricant has to reach from its injection point to the lubrication point. And the more thick it is, the more viscosity it has, the more force you need to move it from point A to point B. So also, the more viscous it is, the more friction loss you'll see. So you see, everything at the end that comes up to a calculation of energy and efficiency, how less energy you can use to get how more efficient system. Okay, and viscosity plays a very important role in that study. Question. Okay, so these are just a few industries that uses viscosity extensively. Just go through them. All right. Now, the definition of an ideal fluid. Who can give it to me? Anyone? Okay. So, well, as I told you that when you're deriving an equation, it's great if you don't have to worry about anything else other than the parameters that you want to get and that you are getting from your experiment directly, right? It's so fun. Like if you know a straightforward equation where there is a property of the material, then you have the you have a constant property of the material. You have a parameter that you are applying to that material, and you are looking for an outcome, right? So all you need to do is just these two things: the property and the parameter that you're putting in. But that's only in the ideal case. In reality, it's the properties are not so straightforward. The properties are not similar over different range of input parameter or external parameter. So there is a huge difference between ideal fluid and between real fluid. And why is the difference? Because we always assume that in ideal fluid, it doesn't have any, its viscosity is constant, meaning it's inviscid, okay? Meaning you're not losing any energy when you're using an ideal fluid because of its viscosity. But that's not true. Viscosity is a very real phenomenon which exists that we all can very well see. And another phenomena is incompressibility, meaning the density of your liquid will not change over pressure, okay? The density is always constant, which is also not true, but it's not the scope of this specific experiment. So what else viscosity can tell us? Well, as I told you that it tells you two things. One, how much energy or how much force you will need to start steel fluid moving, and how much velocity or how much displacement you can get for a certain amount of force that's being applied to it. Now, these two properties, they're kind of like two ends of a telescope. Same rays of light goes from one end to another, but if you need to, like, if you look from one end and if you look from another end, you need to do different calculations to measure properties, but it's the same specimen, or it's the same light rays, right? So your dynamic viscosity and kinematic viscosity, they somewhat share similar characteristics or similar definition, sense of definition, but in reality there is a difference. Your dynamic viscosity, or what is called absolute viscosity, is a measurement of the fluid's internal resistance to flow, which is what I've been explaining so far till now, right? That's dynamic viscosity. And kinematic viscosity is when your fluid, it starts to move, okay? Or when you have when you know the dynamic viscosity of a liquid, for 1 unit of density, how much viscosity the material or the fluid is giving. Dynamic viscosity is important when you need to know how much force you need to apply to make a liquid moving. For example, let's say you want to figure out how much force you need to keep a fluid moving at a certain rate, let's say, 1 meter per second, how much force you will need? Well, it's pretty straightforward. You just need to know, you know the outcome that you want, and you know a constant viscosity that you want. You know a constant viscosity, that's a property of the fluid. So just plug them in this equation, and you get the tau, which is the stress or force over the area. So you get the force that you need. Now let's say I'm telling you, hey, this much force I can give you. So what's the rate I can get? Now this is where you face an issue, you face some trouble, because you all know that force is equal to mass multiplied with acceleration, and acceleration is a function of velocity. So you know the force, and somehow you can reach to velocity. However, there is a mass in the middle, and there is no way you can jump from force to the velocity or the displacement without knowing the mass. So you need to include some parameter that will take care of the mass. Okay? And this is where the sense of kinematic viscosity comes in. So when you divide the dynamic viscosity with the density of the fluid, this is when you get kinematic viscosity. If you notice that the unit of dynamic viscosity is pascals per second, where kinematic viscosity is meters squared per second. So your dynamic viscosity tells you what pressure or what resistance, which is what resistance per second your fluid can provide you, right? That's what your dynamic viscosity is telling you. And your kinematic viscosity is telling you how far it can move per second, and it doesn't really care about the force. For this equation. Okay, so it's telling you its diffusion rate, in other words. All right. Any questions so far?
I have a question. What would be an example of an ideal fluid?
Well, an example of an ideal fluid, you can say when you have a regular gas, let's say nitrogen, and you put temperature in it, you put heat in it, eventually that its volume gets so big that the nitrogen particles, they don't have any affinity or any influence on each other. Okay, in that case, they're not affecting the flow of like one particle is not affecting the flow of another particle. So there is no viscosity in it, and there is no effect on the particles except the external force that you're putting in. Okay, so that can be an ideal fluid, but that's laboratory made. You can't find it in nature by itself. Is it a good example? Does it answer your question?
Yes, thank you.
Okay. All right. Okay, so now different methods of measuring the viscosity. There are a few names up there. First one would be Jane cup. The concept is pretty straightforward. Take a bucket, make a hole at the bottom, let the fluid slip through the hole, and just measure the time, how much time you need to empty the bucket. The more time you need, the more viscous the fluid is, and they usually mostly use it in a painting industry. Then comes the falling sphere viscometer. The concept of it's very common, or it's very similar to parachute dropping, like paratrooping. Can you guys tell me like why or how whenever like a paratrooper jumps in from the plane, how does the parachute work? Or you know, how does the fluid that works on him? Why at a point that they kind of like seem stable in the not stable like this you know, I'm looking for the right word. They feel weightless. That might be a right word. Yes. At what point and why do they feel weightless? Can you tell me? Anyone?
Is it because the resistance of the air on the parachute? Like,
Correct. Mm-hmm. So whenever something is flowing through a liquid, it faces a resistance force from the liquid, and when something is dropping into the liquid, for example, like this steel ball, what's happening that the gravity of that ball is pushing it down. It's trying to drown it more and more. However, the buoyancy force of the liquid will try to push it up. So at one point, the weight of the ball and the and the buoyancy force of the liquid is going to be same. It's going to be equal. At this point, that material or that ball is just going to float into the liquid, you know. So same thing happens when somebody jumps from a plane. The air is a fluid itself, and it has a buoyancy force, right? And it's gonna try to like push the paratrooper upwards, and its weight is gonna try to pull it down. And why the buoyancy happens? Well, it's a resistance, and the resistance comes from viscosity. So definitely buoyancy has to have a link with viscosity, right? So you can say that however much force your steel ball is seeing, it's a function of viscosity. And Stokes, he defined the equation up there. So you can use this equation to figure it out. Then there's another one, vibrational viscometer. The concept is pretty simple. A vibrator is being vibrated in a liquid, and there is a sensor that measures the displacement. And the more force you need to vibrate a vibrator at a certain speed or frequency, the more viscosity the liquid has. Right? Pretty straightforward equation. So that's also a very popular method of measuring the viscometer. But the one that we're going to use is the rotational viscometer. It's very accurate, and this sensor or this system, it gives out the result in torque, right? And if you can remember from the previous slides, that torque has a great impact in the measurement of viscosity. So the way it works, you see that cylinder in here and that plate, the circular plate in there, right? This is modular. It can be changed. The diameter of this plate can be changed. But this outward cylinder thing, it stays constant. I mean, it stays still. It doesn't move. This cylinder does. And you put a beaker of liquid in here. So that cylinder is submerged into that liquid. And then this cylinder rotates. This cylinder stays still. So like the first example that I was giving, where two plates, liquid is stuck between a steel plate and a moving plate, it kind of imitates a condition like that. So there is a torque developed between the steel plate and a moving plate. Moving plate will try to move the liquid, and steel plate will keep it still. But since there's a difference in velocity, a torque will be induced. And to keep the cylinder moving at a certain velocity, the more force you need, or you can say to keep the cylinder moving at a certain angular velocity, the more force you need, the more torque you need, the more viscous your fluid is. And it all can be derived from this equation. I'm not gonna derive that equation, but whatever I told you guys so far physically, this is what's being written mathematically in this equation. And you can see that it has a term Ri, or hold on. Yeah, it is the R naught. Okay, this time. So this is the diameter of this plate. So the more diameter it has, the more fluid is gonna be in contact with the surface, and the more force you need, right? So you can get all these things from here. You can figure out the viscosity using this equation. All you have to know is the angular velocity, the torque that you are applying, and you know the R naught, or the diameter of your cylinder, and all the other parameters like the dimensions of the whole setup. So in your report, when you're gonna write your methodology section, make sure that you mention each section and what its importance for this specific experiment. All right. For example, you can say that this cylinder it moves, and it's a crucial part to create the torque. Just an example. Okay, so this is how the actual apparatus looks like in your lab. That's the beaker, and this is a heated plate that will be used for the second part of the experiment. This is a temperature control section. With this section, a constant heat with time, or a constant temperature with time, can be provided. And just like boiling water, the liquid will start getting heated up from the bottom layers to the top. Okay. All right. So I've noticed that whenever you guys are explaining different your deviation in your results in your reports, you guys always say it's a very common measure or common reason of error is that the apparatus is old or human error. Okay. All right. Yeah, that's all true. I mean, this adds into your deviation, but there are a lot other physical or scientific reasons that also can cause the deviations. For example, over here, your beaker is getting heated up from below, right? So the bottom layer will get heated up first, the top layer will get at the very end, and so on for the layers in between. Now, if you just measure the viscosity in here, is somewhere in the middle, while your plate is being heated up, definitely you're not gonna get one viscosity that describes all the points of this liquid. Okay, if you measure the viscosity somewhere near to the plate, you get something different result. Somewhere at the up, you get more thick liquid. So that could have been one reason for your errors, and that's a scientific reason. That's not that's not like a technical or non-scientific reason. Like not a negligence. So I want to see more and more reasons like that in your report. So how can you resolve that error? How can you have a constant uniform viscosity throughout the whole beaker? Well, it's pretty simple. All you need to do is break out those layers and mix with one another. How can you do it? Using stirrer, that that stirs by itself. You don't have to use a spoon in the liquid and just mix it all the time. That's very super inconvenient, right? So we use metal balls, small metal balls, and it goes into the liquid. And this plate, it has a magnetic field, magnetic capability as well. So it can move that metal steel ball inside the liquid. And since that ball is moving, so it's going to break up the layers, and you will have a uniform viscosity throughout all the sections. Any question?
No questions.
So these are the procedures. Insert the viscometer, stir into the oil, turn the motor on, observe the viscosity. Then first experiment is done. Go to the second one, heat up the plate, do the same thing again, and but do that with different temperatures, increasing temperature, and break up the layers, use a stirrer, and again record the viscosities and make a comparison. Okay. There's a YouTube video up there. It explains the experiment if you want to go through it. Okay. Now, what I'm asking you from your report, a few tables, definitely. The first one, you need to plot a graph between viscosity and the test number and discuss its behavior, meaning you find results for may or may not be for different liquids into the data pool. So the reason of getting this plot with test number is to see which oil was used for what experiment. Okay, so as you get different viscosity at different test number, you can compare those viscosities with the already proven viscosities online, and just you can make a table telling, hey, this liquid is used in experiment 1, this one is in number 2, this one is number 3, or maybe all liquid are the same liquid. Okay, but which one is it? All right, then comes a viscosity versus temperature. So that's without the stirrer, like you haven't started changing the temperature. So see how when there is no heat sources available, or you're not using a stirrer, how the viscosity is changing with temperature, and why is that? What property or what phenomena can be used to describe that such behavior? Then comes the second method, second stage of your experiment, where different temperatures are being used. So I will ask for a curve that has a viscosity versus the temperature. Okay, and you have viscosity versus temperature without the stirrer, and viscosity versus temperature with the stirrer. So you can do a comparative study of how breaking down the layers, or how having a stirrer gives you a different sets of results, and which one do you think describes the characteristics of viscosity, or describes the parameter of viscosity better for one liquid? Why one is more acceptable and another is not? Okay. All right. So that's it. Do those comparisons, make those graphs, do those calculations, and that's it for your results and discussion section. And these are the data that you're going to get from the experiment.